棒のトマト、棒のトマト、棒の棒のトマト、赤上げて緑下げてトマトマトマト。
Today, in trying to understand how the universe works, are describing it mathematically. In their equations, they use so-called fundamental constants. These constants are at the basis of their theories. We've seen in a previous clip that there is evidence that two of the fundamental constants, c, the speed of light, and big G, the gravitational constant, fluctuated over time. Today, we'll have a quick look at h, the Hubble constant. Enjoy. Blah la land. You are guilty until proven innocent, even if you use other people's work for educational purposes, commentary and critique or satire. Therefore, we sometimes have to resort to artificial solutions, like avatars and voiceovers to overcome this. Let's see if it works. Here, I will quote or paraphrase Professor Mike Merrifield from the University of Nottingham, talking about the Hubble constant. There was a group of astronomers who all thought it was 50. A group of astronomers who all thought it was around 100.
Ever since Edwin Hubble discovered that the universe is expanding, there has been a great debate about the speed of this expansion, also called the Hubble constant. In 2000, scientists thought they had reached a consensus with the Hubble constant at around 72. But since then, two methods of calculating the expansion rate have grown farther apart. Some scientists think it's too big of a difference to just be a statistical fluke. To calculate the Hubble constant, we need both a velocity and a distance. Velocities are easy. It requires the measuring of the redshift of a receding galaxy. But distances are harder. We need standard candles, objects that shine with an intrinsic brightness. That way, its observed brightness can be converted to a distance. The first method to calculate the distance originated with Hubble himself. He started by measuring the distance to nearby objects and working his way out. Hence the name, the cosmic distance ladder. Linking all these measurements, a recent study pinned the constant at 73. Instead of starting within our galaxy and looking out, the second method looks back in time to almost the beginning of the universe. Recent estimates are at about 68, significantly lower than the cosmic distance ladder's approach. Both camps hope to resolve this debate in the coming years, with the help of new telescopes and instruments. But if the discrepancy in the Hubble constant remains, it could mean that our understanding of the expansion of the universe is missing an ingredient.
There was a big argument running for decades. And these two camps were at war with one another, coming up with more evidence to support their argument and to trash the other's ideas. Quantity, the Hubble constant, is really a measure of how quickly the universe is getting bigger. The equation is that v, the velocity that things are running away from you at, is h, the Hubble constant, times d, the distance away. And is just a number. And it's unfortunate that astronomers are measuring it in really strange units. When usually measuring velocities of galaxies, the unit we use is kilometers per second. Distance to galaxies are typically measured in megaparsecs, millions of parsecs. The constant has those weird units of kilometers per second per megaparsecs. And in those strange units sits a number that comes out at somewhere around 70. Constant is not really a constant. It's a bit of a misnomer to call it a constant. Actually, it's changing with time. Simply, it's a measure of how fast the universe is expanding. There are various forces acting upon that expansion, and the pull of gravity is trying to slow down that expansion. More recently, we've discovered that mysterious thing called dark energy, which is actually making that expansion speed up with time. That this constant has actually varied over the lifetime of the universe. In order to understand exactly where we are, usually, instead of just calling it h, we call it h null. Say, that's the particular value of the Hubble constant as it is today. It's only within the last 5 years that we've really measured it. Measure the Hubble constant as it was in the past, or how it's going to be in the future, it's something that we're really struggling to do. Probably one of the next great things in astronomy, at least in cosmology, in understanding how the universe works on a big scale. How this constant is evolving with time. Value is pretty well tied down. Official sanction value. Different people use different values. It's important that when you use it, that when you write a scientific paper, you say what value of the Hubble constant you actually used, so when people disagree with you, they can always go back and redo the calculations.
Hé, come c'est la tomate!